We have a twice differentiable function of f and g, and they are defined for all numbers x. And the values of f and f prime for the values of x are given in the table. There's actually no g in here, actually, it looks like. Okay, so find the x coordinates of each relative minimum of f on the interval, and then justify. So I've got my table here, and I'm going to plot my x and y coordinates based on the table. So at x equals -2, y equals 12. So I'm going to maybe over here at -2, maybe draw -2 somewhere around here. It's going to be a y coordinate of 12. At x is -1, my y coordinate is 8, so maybe I'll draw it somewhere around here. At x equals 1, the y coordinate is 2, maybe somewhere around here. And at x is 3, the y coordinate is 7, so maybe somewhere around here. And what it also tells me that it's positive throughout, so I know it never crosses the x-axis. Okay, so I want to make sure that I notice that part as well. So there's my coordinates. So then I'm going to do a slope chart. Doing a slope chart it's going at -2, it's just going down to start. And between -2 and -1, I know I have a negative slope through here. At -1, I have a 0 slope. So it looks like that could be a possible minimum, but when I go between 1 and -1, it stays negative. So it just keeps on going down. So it looks like that is a slide through that point. And then at +1, I have a slope of 0. So again, that's a potential minimum point. And then on this side, between 1 and 3, it is positive. Okay, so it's going up. So that looks like we have a relative minimum point at x equals 1. And then finishing off, it's still going up. Maybe not at the same rate, but it's still going up. Okay, so that's what my graph looks like. And from this, I can justify that there must be a minimum point, a relative minimum from the graph. At x equals +1. Okay, and +1, y equals 2. So if I sketch my graph in, it's going to go through here. It's going to slide, come down. It's a min, and then it's going to keep on going up through there. Okay, so there's my graph, and I have a justification based on my slope chart and also my graph. All right, so part B says, explain why there must be a value C for the interval -1 to 1, so that the second derivative equals 0 at some point C. Okay, so this seems like either mean value theorem or intermediate value theorem. Now this is mean value theorem, and we can use mean value theorem because it is twice differentiable. So what that means is that f is smooth and continuous, but it also means that f prime is smooth and continuous. So this then satisfies the condition for the mean value theorem if we want to use this. Okay, so we don't have values of f double prime, so we don't know if f double prime is continuous. So we can't actually use the intermediate value theorem. We're going to use a mean value theorem, and we're going to do it this way. Okay, so the first thing is, so this is for part B. The first thing is I'm going to find average slope. So if I find the average slope between -1 and 1, my average slope is going to have a slope of 0, so the average slope through there is going to be 0. Okay, so the first thing is I'm going to find the average slope. So the slope of the slope. So the average slope of f prime is equal to 0 minus 0 over 1 minus -1. So it's going to be 0 over 2. So the average slope of f prime equals 0 over that interval. Okay, so and that's over the interval -1 to 1. So what that means then is that I can apply, say that the average slope is going to be relate to the second derivative slope, okay, or the second derivative. So the second part of this is, I know that the f prime graph is smooth and continuous, okay? It was because of that differentiability, the second twice differentiability of the f function. Okay, so since it's smooth and continuous, now I have the condition to apply mean value theorem. Okay, so therefore, by the mean value theorem, okay, we know that the second derivative, or the slope of the slope, there must exist some point on the slope of the slope graph equal to 0, and must exist. We know that this must exist. Okay, and where c is in the interval from 1 to -1. So that means that the average slope of the f prime graph is going to be found as an instantaneous slope on the f double prime graph. Okay, so we have to kind of think in a few layers here. The f prime is the actual graph that we're looking at. The f prime double prime represents the slope of that graph. So then we can apply mean value theorem in this case. Part C says then the function h is defined by ln f of x, and we want to find h prime of 3. So this is a problem where we need to differentiate notation. So if I want to differentiate notation, then I'm gonna differentiate that h prime notation. Sorry, the h of x notation. So h of x is equal to log f of x. If I want to find the h prime, well, this is an embedded function, so I'm going to differentiate 1 over the inside function. But because the inside function is a function itself, I need to multiply that using chain rule. So I'm just going to simplify this. So I have a now expression for the derivative of h prime expressed in terms of f prime and f of x. So if I want to find the value of the slope at that point, well, I go back to my table at x equals 3. Okay, I need an f prime value at 3, which I have. So f prime at 3, that value is 1/2. Okay, so that's my f prime at 3. I also need an f of x value at 3. My f of x value at 3 is going to be y equals 7. So plugging those values into my expression, I can then find the h prime value at 3. So h prime of 3 is then equal to 1/2 over 7. And I'm getting those values from my table. So that means that the derivative of whatever the h graph is at 3 is equal to 1 over 14.